Team 17 was tasked with building a Mars Cargo Mobility System, or MACRO for short. With human travel to Mars becoming more and more likely each day, being able to have some infrastructure on Mars is crucial. Building a cargo system to aid human explorers on Mars receive various supplies will allow for more time to research this new planet. In order to do this, the macro needed to navigate precisely, recognize and react to obstacles, deliver cargo in a timely manner, and bring the cargo from location to location without tipping. This presentation will be showcasing how the macro was created to perform these basic tasks autonomously. In order to see how the macro was created, one must look at the management process. Team 17 used a Gantt chart to organize the development process. The Gantt chart provides about a week and a half to research and brainstorm. After the brainstorming period, there's a 2-day design period. A week and a half period was built in to create both the code and the macro itself, as well as to test it. After this testing period, the results would be evaluated to see where the design could be improved. After this evaluation, the second testing would begin and any final changes would be made. Customer needs: precise navigation, handling obstacles, recognition of hazards, handling of terrain, delivery of hardware, and transporting cargo without dropping or tipping. To meet these customer needs, the macro had to be 0 inches away from the drop zone. It had to recognize hazards from at least 3.5 inches away. The macro had to get over an incline of 30 degrees. It had to complete a lap around the track in at most 2.5 minutes. And the cargo space should be 130 millimeters wide and 130 millimeters long, with a height of 80 millimeters, and hold at least 975 grams in the cargo space. In order to visualize how the deliverables would be split up, the work breakdown structure was designed with building, coding, testing, and documenting the design process. Of course, the deliverables mean very little on their own, so a functional block diagram was developed. The functional block diagram connects each of the systems in the work breakdown structure. The macro should be able to take in sensor data, the path choice, power, cargo, and the program, and use the computer to activate the movement system and bring the macro to the final position and deliver the cargo. The functional block diagram leads us to our initial.
In the early planning stages for the macro, it seemed that the cargo unloading mechanism would be the most complicated feature to implement, so that was the main focus of the brainstorming session. Ultimately, 4 design ideas were proposed for the final design, depicted in these figures. All 4 designs had nearly identical frames, wheel structures, and sensor placement, with the only difference being the method used to unload the cargo and the placement of that mechanism. Design idea 1 involved a lift mechanism similar to a forklift, which would be attached to the rear of the macro. Design idea 2 featured a trapdoor device in the center of the macro, which would then drop the cargo and then drive over it. Design idea 3 had a similar mechanism to design idea 2, but in this case the cargo holders would be placed on each side to allow for a lower height and even weight distribution. Lastly, design idea 4 was similar to a dump truck because it would tilt the cargo in a bed and then release the cargo so it would slide out. A decision matrix was used to determine the optimal design for the cargo unloading mechanism. The designs were judged on 4 customer and technical needs. The macro could not be too tall, so this was measured by a maximum required height of the macro. Also, the macro had to be well balanced, which was measured by the ratio of the mechanism's radial distance from the center of the macro to the total length of the macro. The macro had to be built in adequate time, so this was measured in estimated build time, and the design had to be simple, which was measured by the number of motors required. For all of these specifications, lower values were more desirable. After all the estimates and calculations were put in the decision matrix, it was determined that design idea 1, the forklift mechanism, would be used. The main structure of the macro turned out to be simple to build, as seen on the right. It had front-wheel drive for ease with turning, 1 sensor on the front with room for more sensors, and space on the rear to place the cargo. The initial cargo mechanism, however, proved to be a challenge. It was realized almost immediately that the forklift design would be much more complicated than it originally seemed, because a track would have to be constructed for the lift to move up and down, and gears would have to be placed very precisely to operate effectively. As seen on the left, a modification was made to the design. Instead of having a lift that moved vertically, the structure could be used as a stationary platform with gears on the side, which would push a horizontal bar that would push the cargo off the platform. This, too, turned out to be very difficult to construct for mostly the same reason as the forklift. The track for the moving parts to go along would be very difficult to keep stable. As a result, an even simpler solution was developed as seen in the center. This unloading mechanism consisted of a shaft sticking vertically out of a motor, with two horizontal bars attached perpendicular to each other. Ideally, one bar would keep the cargo in place, and then when the macro reached the drop zone, the motor would spin and the second bar would push the cargo off the cargo platform. After comparing the macro with the dimensions of the cargo, it was determined that a much larger cargo holding platform was needed. Additionally, after testing the cargo unloading function, it was observed that the spinning mechanism only needed one horizontal bar to hold the cargo in place and push it off, with a barrier added on the opposite side of the platform to guide the cargo straight off the back. A ramp was added to the rear of the platform to allow the cargo to slide down and land upright. Line finders were added to the front so the macro could follow the paths. A gyro sensor was added to the side to detect inclines, and an IMU was added to the other side to detect the magnet at the cargo drop zone. Several other features were experimented with. The macro had trouble getting over obstacles, so it was fitted with larger wheels and a gear system to increase its speed. However, the wheel size made it more difficult for the macro to turn, and the increased speed made the macro's line finding less efficient, so these changes were ultimately rejected. The IMU was moved to the front of the macro to be in a better position to detect magnets, and the line finders were moved to the center because this allowed the macro to stay on the line better while turning. These changes were kept. The final design featured an IMU and ultrasonic sensor in the front and line finders in the center. These were the only sensors that were needed because the IMU functions as a gyro sensor as well as a magnetic field sensor. The macro had to sacrifice speed and power for maneuverability and ability to follow a line. The cargo removal mechanism was simple but powerful and effective. The fact that the macro was very low to the ground and had trouble getting over obstacles was not ideal, but there had to be trade-offs. The final design was the best combination for efficiency and reliability. The programming went through several developmental stages as well.
In the design process of programming, it was vital to make sure that the robot could go over the obstacle, follow lines effectively, drop the cargo at the correct target, know what to do at intersections, keep the cargo stable on the robot, speed up on ramps, and stop when it gets back to the landing zone. In order to go over the obstacle, the robot had no mechanical advantage in passing over the obstacle at the cruising speed, so the code had to make the bot start off going at a high speed in order to have a chance at going over the obstacle. So the code first executes a command to run the motors at a very high speed, and the robot sleeps for about 2 seconds. And after these 2 seconds are over, the main loop is executed. After this, the main periodic loop of the robot would start, and the robot would start following the lines. The robot follows the lines by turning left when the left line reader detects the black line, and it turns to the right when the right line reader is detecting the black line. It is set to do these turns stationary so that it could not accidentally go off course in the scenario where it is turning and moving, and it will also do these turns as quickly as possible so that time is not wasted. So the code here says that a while loop will be executed while the left line is detected, and if both lines are detected, it will break out of the loop because a different command needs to be executed if both are detected, and at the very end, the direction it needs to turn is executed. When the robot goes to the intersection, it would turn in the correct direction to go to the desired target. It does this by detecting when both line finders see the line. And then it turns in the correct direction. It is predetermines what target the robot has to go to, and all 6 possible targets are considered in the code. Whenever the robot comes to an intersection, it will iterate a variable that stores how many intersections have been encountered. A series of logic statements evaluate what to do depending on how many intersections have been encountered and what the ultimate target is. So if the robot needs to go on the second target on the right, the robot knows that it must first go straight on the first intersection, right on the second intersection, left on the third intersection, straight on the fourth intersection, and right on the fifth intersection. When the IMU unit detects the magnetic field of the magnet below the target, the code will start up the dropping mechanism, which will slowly push the cargo as the robot moves. As the robot was accelerating, the dropping mechanism would turn the other way to keep the object on the robot in case it slid out. And this is shown in a flowchart. Deploy cargo is a function that executes, and it sets a variable called magnet minimum to a value, and this is the minimum magnetic field to start the dropping process. And there is a decision that compares the current magnetic field detected to the desired magnetic field, and if the detected is greater, then it starts the dropping mechanism, and if it doesn't detect it, then the dropping mechanism is stopped. Here's a flowchart showing how the robot keeps the cargo in the holder. It first makes sure that the acceleration magnitude is greater than a certain amount, and if it's being deployed or not. And if both of those conditions are fulfilled, then it will push on the object in order to keep it in. When the robot came to a ramp, we detect changes in negative acceleration. And if a significant negative acceleration was occurring, it would speed up for that duration. And finally, when the robot returns to the landing zone, it will listen for the magnetic field, at which point it would stop and wait for cargo.
For both the robot's overall performance and design, there were positive and negative aspects. In terms of the positives, the main one would be the unloading mechanism. The cargo holding system was large enough and met all target values in order to individually carry each of the 3 types of cargo. The robot was able to maneuver around the practice course while carrying the cargo. The bot would not tip or turn any different despite carrying a large load in the back. Throughout all the tests, the unloading system was able to deliver each of the 3 cargo objects within the desired radius of the drop zone. The cone, cylinder, and block were dropped upright and would slide a little but remain within the designated location. During testing, the bot could carry each individual object easily, and a max test mass of 475 grams was achieved, enough to carry the largest object. Another positive of the bot was its ability to achieve a desired speed. By testing different powers for the motors, Team 17 was able to determine the speed of the robot at certain powers. The team measured how long in seconds it would take the bot to travel 150 centimeters. In doing so, the team was able to determine a trend between the speed of the bot and the power being used in the motors. By graphing this trend in Excel, the team was able to find an equation to represent the relationship between the motor power and the final speed. By plugging the desired speed into this equation, as shown in the example, the team was able to determine the necessary motor power for the speed run. By directly inputting this calculated motor value based on the desired speed into the straight line program for the robot was able to complete the speed test with great accuracy. Although there were many positives for the bot, there was also a fair number of negatives, the biggest being the line follower program. Despite occasionally working in testing, the line following system was incredibly inconsistent. The robot did fine on straight, solid lines, however both dotted lines and curved lines were challenging and would not work all the time, including during the final test. The most problematic areas of the final test map are circled on the 2 map images. Since the line follower was not working right, the robot could not complete any of the tasks required of it on the map. The issue for this came from both the code and actual build of the robot. The code had issues following the dotted line, and the design itself was problematic on the turns. The code did not account for the change in pattern of the line or alter the speed or turn of the bot for the sensors to work together properly. The robot also had design flaws when it came to moving around the curves while also maintaining its location directly above the line. Since the line follower, which is circled in red, was in the middle towards the back of the bot, the turn radius was lowered and precision was increased. However, to account for the sensor placement, the speed was decreased significantly. Therefore, the robot was forced into far smaller and jerkier motions, causing it to veer off course amidst its small altercations while attempting to realign itself. This resulted in the robot to ultimately spin in a circle slowly with sporadic movements. Although the bot was well equipped to successfully navigate over the obstacle and the hill, it only had a chance to attempt and complete the obstacle due to its problematic line following. During the preliminary tests, there seemed to be few problems with the robot and more positives about it. On test day, however, a few minor problems led to an overall negative performance.
Team 17 was plagued with unfortunate circumstances due to the COVID-19 pandemic, leading to a disconnect between the build team and the code team. If there was any way to improve the macro, it would be time management. If the build process had started just a week earlier, development would be on track to fix the issues discovered during testing. The main area for improvement was the line finding and turning capability. A previous iteration of the line finding was able to successfully navigate even a dotted curve. During the final demonstration, the macro would not be able to get itself back onto the line when making a turn, leaving it to turn slowly, aimlessly in a circle. The macro was able to perform any task individually, but due solely to the lack of turning capability, it was unable to perform any task correctly that involved turning. If the development had started earlier in order to allocate more time to testing and adjusting the macro, the performance during the demonstration would have been drastically different. In order to fix the turning and line reading, the code would need to be revised, and the line reader should have been closer to the front of the macro rather than the center. Although individual components of the macro worked correctly, more time should have been spent on the turning capability to integrate all the functions together.